Today we're going to start graphing, or start out with graphing logarithmic functions, or actually we'll start out by graphing a regular old function. And so when we have this problem, we have graph y equals 2 to the x. So over here when I make my table, we got x and y, and we did this not too long ago in another section. 2 squared is 4, 2 to the first power is 2, 2 to the 0 is 1, negatives mean reciprocal, so that's 1/2, and 1/4. And the function looked like a curved graph that looked like this. In order to graph the inverse, what we want to do is we want to switch x and y, because that's how we find inverses. So we're going to have a point at 1/4 -2. We're going to have a point at 1/2 -1. We're going to have a point at 1, 0, at 2, 1, and at 4, 2. So 1/4 -2 would be about here. 1/2 -1 would be about here. 1, 0, 2, 1, and 4, 2. And the graph looks like this. And what we have just done is the first log graph. We graph y equals log base 2 of x, because logarithms are the inverse of exponential functions. So in general, the rule is log base a of b equals c. That means a to the c power is equal to b. So let's start out by doing some exponents and change them into logarithms. So this would actually be example 2 from our notes. So if I said 3 to the 5th equals 243, if I want to rewrite this as a logarithm, that would be log base 3 of 243 is equal to 5. And the 5, the exponent, is the answer of a logarithmic problem. So for something where we have example number 1, let's do one more of example 2 first. If I did 4 to the -2nd equals 1/16, that means log base 4 of 1/16 equals -2. In logarithmic problems, this number must be positive. You cannot take the log of 0. So if I ever said log base 4 of -2 or log base 4 of 0, these two things do not exist. So I did example number 2 first, so let me go to the next slide and do example number 1, which basically asks us to do log base 5 of 25 equals 2. How can I rewrite that as a exponential function? And so we change it to be 5. The 2 here becomes the exponent, and we know 5 squared equals 25. Log base 9 of 1/3 equals 1/2. That means 9, I'm sorry, that should have been -1/2. 9 to the -1/2 equals 1/3. In example number 3, we're asked to do log problems. And so, in order to do this, I'm going to do 3 times 3 equals 9. That wasn't enough 3's. Times 3 equals 27. And that's not enough 3's. And so I multiply by one more 3 and I get up to 81. So I had 1, 2, 3, 4. What happens if this is log base 4 of 1 over 64? Well, I'm going to still multiply the 4's together. 4 times 4 is 16. Well, that's not enough. Times 4, that turns out to be 64. So it took 3 4's in order to get up to 64. But because this is a fraction, and fractions are reciprocals, that means the exponent has to be negative. Alright, this next problem says we have $8,000 and we're going to compound annually at 4%. How many years till I get to $12,000? So I'm going to put $12,000 over here because that's how much I want to end. A reminder, our equation is y equals p 1 plus r over n to the nt. Now, $8,000 is how much I'm starting with. 1 plus the rate is 4%, which is 0.04, divided by 1, which I don't really have to do, and then we have to 1 times t. So, in order to solve this, I'm going to first divide both sides by 8,000. And this turns out to be 1.5 equals, let's simplify the parenthesis, and I got 1.04 to the t. So what I'm going to do is I'm going to use my calculator. In my calculator, I'm going to do y1 equals 1.5 and y2 equals 1.04 to the x. There will be a way that we can solve this by hand, we just don't have it today. Because it doesn't intersect in our graph, I'm going to make x maximum equal to 50 years. And we can make x minimum equal to 0. So x min is 0 because we know it's not going to be going back in time, and x max of 50, and see what happens now. You can see the intersection, so we calculate the intersection and we find out that it took 10.33 years. I'd round up to 11 probably because it only compounds every year, but I would probably have taken either answer because it shows you know how to solve the problem. Alright, for this problem, I'm going to change this to be x squared equals 9. So we rewrote this only because this x was the base and that's what we're trying to figure out. So at this point we can square root. Now normally I would tell you that this should be plus or minus 3, but the x value cannot be negative here either, so my answer is simply x equals 3. Here are the 4 rules that are on your notes. I shouldn't have written that because it crossed it out, but multiplication is the same as adding 2 separate ones. Second one was dividing, means the same as subtraction. We can move the exponent in front, and finally, if we have 2 logs that are the same thing, then that can just be, we can just basically cancel out the logs. So let's take a look at this one. They both have log base 8 at the very beginning, and it's the only log that they have. So I'm going to simply say that x plus 5 equals 2x. At this point I can just solve for x like I normally would. The one thing I would want to do is I would want to check my answer to make sure that neither side or that both sides are not negative. 5 plus 5 is not negative. 2 times 5 is not negative. And so x equals 5 is our answer. Alright, last problem for this section. Because this has a plus in the middle, we are going to change this to be log base 4 of 3x plus 1 times 5. And we'll put that all in parentheses equals 2. Now, we can't just cross out the log base 4 because there's not one on the other side, so I'm going to have to rewrite this as an exponential. So 3x plus 1 times 5. is now on the right side, and 4 squared is on the left side. So I know this is 16. This is 15x plus 5. Don't forget to distribute this. Subtract 5 on both sides. 11 equals 15x. Divide by 15. And 11 over 15 equals x. So when you do this, and you check this, it's going to turn out to be okay. Nothing's going to be negative, and so we have our final answer. And that was 11-4 logs.